Thank you all for joining this afternoon's webinar. My name is Dan Montano. I'm a technical specialist with SolidCAD, and we will begin shortly. Thank you all for joining this afternoon's webinar. My name is Dan Montano. I think we should get started now. This afternoon we'll be talking about settling and non-settling slurries in FluidFlow. Online as well with me is my colleague Robert Piccinich, Industry Account Manager. Please type in your questions in the chat window. Robert will watch that, and we're gonna try to answer them in the chat or by email after the webinar has ended. Couple of words about SolidCAD and Fly software for those of you that maybe do not know who we are. And settling slurries approaching FluidFlow and non-settling slurries correlations are going to be the next two topics, interspersed with a couple of examples. So I hope you'll find this interesting, and let's get going. SolidCAD is the first Autodesk Platinum partner in Canada, currently part of the Cancel group, and SolidCAD established in 1996, Cancel in 1966, and together since 2005. So as the largest Autodesk Platinum partner in Canada, SolidCAD has a team of over 100 professionals, technical and sales and support. And we are offering technology information services in a number of industries: AEC, civil infrastructure, plant and process, manufacturing, and media and entertainment. As part of our activities, here's a list of some of the more important ones: training, BIM consulting, data management and collaboration, scan to BIM services, technical support, software development, simulation and analysis, PLM, product lifecycle management, workflow optimization. Coverage coast to coast in Canada, currently in 15 offices and 12 training facilities, an academic authorized training center. And as I mentioned, as part of Cancel Group, we have access to an even wider range of software and hardware technologies, including plotters and printers, wide format plotters, mapping and GIS solutions, construction supplies, and surveying equipment. I mentioned SolidCAD is Autodesk Platinum partner. We do partner with other technology companies around the globe. Obviously, the subject of today's presentation is FluidFlow, created by Flight Software in Northern Ireland. So, a company established in 1984, the first year of launching the first release of piping system FluidFlow, an ISO 9001-2008 software company, with the ability of also creating number of customized software solution, and here are some of the customers that employ that type of capability, customized solutions on top of FluidFlow. So Fortis in BC, Sterling Fluid Systems, and Weir Group as a few examples. Here's a list of some other companies, and you're going to recognize some large technology companies here, and a full customer list available at the website listed, and a couple of testimonials from our own customers at SolidCAD that use FluidFlow solutions for a number of years now, and the positive effect it had on their business, on their deliverables. Now, the current version of FluidFlow is 346, and I want to take a minute here to explain you a few things about the software package, the way it's built. So it's basically a single flow sheet type calculation. A number of databases are supporting the different fluids and components, and it's a modular solution, a modular package. Liquid module, gas, non-Newtonian and slurry, two-phase, and scripting are the 5 modules that you can work with. Obviously, there are some prerequisites here. For example, on the settling and non-settling slurries, you would be requiring to have the liquid module as well. I mentioned the databases. You'll see some of them in action there. Fluid database, the solids database specifically. Some other capabilities, equipment auto sizing, and Flight Software being an ISO certified solution. Company. You'll see a set of quality assurance files also delivered with a program. And the common feedback from customers is how easy it is to learn and use, and how quickly you can become productive with FluidFlow. So specifically, we're going to be talking about the non-Newtonian and slurry module. Here are some of the applications in terms of mining and the mineral processing. So hydrotransport after comminution, or mine tailing systems, wastewater, dredging, as well as other non-industry, from other industry specifics like pulp and paper, stock, and food processing. Some of the things that you're going to find interesting here: pump derating and power usage as output, calculation of solids delivered, the calculation of deposition velocities to identify if sanding or a blockage occurs in a pipe, and also the capability of allowing you to get more insight in how your system works, to be able to maybe identify some energy saving opportunities or potential operation issues. Okay. Now let's take a look now at the 2 main chapters here. So the settling slurries or heterogeneous slurries, and later on the non-settling ones. So when we talk about settling slurries, we basically talk about solid particles in either a full or a partial suspension in a Newtonian liquid as a carrier, as a transport medium, and that Newtonian liquid is usually water. It doesn't have to be water, but that's the typical carrier we deal with here in these two industries. So what can we do with fluid flow? Well, for example, fundamentally, we're interested in pressure losses in the system. We're interested in flow characteristics, velocities, flow rates, to be able to reduce the possibility of blockage or saltation or sanding, as it's called. We use FluidFlow to help us with pipe sizing or to get information about the quantity of solids delivered per unit time based on a certain weight concentration of the heterogeneous mixture. So what's important here is it's basically the fact that we first of all need to figure out if the slurry is a settling one or a non-settling one. So solid characteristics that are accurate are going to be important here. To determine the friction losses, there are some factors in play. The fluid properties, which is going to be defined in the fluid database as a carrier, as a pure Newtonian liquid. The solid properties, and there are some thermal properties of the solid that could be interesting as well. By the way, you might have noticed a note there that thermal module is included with all the fluid flow modules. But as far as friction losses here, there are some solid properties which are important. So, for example, a shape factor correction, which is going to account for non-spherical particles. So basically, it will take into account the difference in settling velocity between a solid of the same diameter, function diameter, in the shape of a sphere, and the one that's of an irregular shape. There are different shape factor definitions in literature, but FluidFlow uses the Clift shape factor, as you'll see later on, there's a setting in the options that we can turn off. It's off by default, in fact, to allow for this kind of shape factor. Some other important properties of the solid, and these are defined in the database, solid database. Bed sliding coefficient, and we'll talk about that in a bit more detail later on. Particle size distribution, D50 and D85 sizes, the solid concentration. So all these are going to be defined on the inputs on the flow sheet, on the input, on the inlets. So, and lastly, sorry, pipe inclination, which if below 30 degrees, it's going to be assumed horizontal here. So these are the important factors that we need to consider in determining friction losses in a system. Here are some screenshots of the different databases that FluidFlow supports, comes with in terms of out-of-the-box content, and these databases are fully customizable, so you would be able to define your own fluid, Newtonian or non-Newtonian for the non-settling type of slurry, your own type of solids, as well as different components, boosters, valves, and so on. So in terms of settling slurries, there are 5 pressure loss correlations built into the current version of FluidFlow. Here's a screenshot of the relevant section of the options window. The different correlations, let's talk a little bit about those. There is a default one here, then the third one, Wilson, Addy, Zellgren, and Clift, and we'll get to that. But just a few words about each of these correlations. So the Durand, or also Durand correlation, also known as Durand, Condorcet, and Worcester. It's basically the simplest model. It will require the D50. So D50 is mass mean particle diameter. So it's basically the screen size or sieve size if you take the solids and get them through a screen of a certain size, where the 50% of the particles would pass and 50% would be retained. So that's the screen size value. No distribution data is going to be used in Durand correlation. The Durand coefficient in Durand equation value could also be adjusted to other than the default value of 52, but this is the default value used by FluidFlow, and it's typically an unknown anywhere between 65 and 150. An extension of Durand method is the WASP correlation by Edward J. Wasp. It moves up from the D50 to a full size distribution data, and still uses Durand correlation for friction loss calculation with that Durand constant value, also of 52. I was saying earlier the default FluidFlow value is actually the WASC, and I'm sure you recognize the cover of the one of the more important literature reference books here, the slurry transport using centrifugal pumps by Wilson, Addy, Zellgren, and Clift. And this will require both D50 and D85, where D85, 85% by mass particles are finer, and the solid bed friction coefficient defined earlier in the solids database. And it can include the inclined pipes anywhere between -20 to 80 degrees. It assumes that the flow happens in four regimes: homogeneous with non-settling tendencies, pseudo-homogeneous for a bit larger particles, 40 to 200 microns in size, heterogeneous, which is kind of where we want to be most of the times, in 150 to 400 microns type particle, and fully stratified or sliding bed, coarse particles, low velocities, possibility of blockage and saltation. So a flow regime that we're trying to avoid. Also, FluidFlow will plot the Rosen-Ramler distribution curve. You can get your D50 and D85 from there if you actually happen to have a full size distribution and want to use the WASC method. And this curve is available on the chart tab on the results. A couple more models here available. The 4-component model of Zellgren and Wilson. It's basically a combination of carrier fluid, pseudo-homogeneous mixture, heterogeneous solids, and the fully stratified solids. Lastly, the Liu de Jong pi-friction loss model, which is a 2-component model. Smaller particles form a pseudo-homogeneous carrier, and the larger particles are assumed a heterogeneous suspension. The important part with this model is it's actually a concentration based, not a particle size based. So it looks at variation of mixture concentration across the pipe diameter from the pipe center line. Now, an important output measure here, it's going to be the limiting velocity. So it's basically the let's think about it as a smallest fluid velocity, mixture velocity that your system one could be at to ensure that there's no possibility for saltation. So FluidFlow will generate two deposition velocities there. So for one for the limit of stationary bed, VS in this curve from this graph from the slurry transport book I mentioned earlier, and the VSM, the maximum limit of stationary bed, which is the actual deposition velocity. So again, output measures automatically generated by FluidFlow. So the maximum deposition velocity, maximum limit of stationary deposit, defined as deposition velocity in FluidFlow there. It's the velocity that represents the point at which no settling will occur, regardless of solid concentration. So basically, what we're doing is we're eliminating the solids concentration variable there, and this way we're making sure that no saltation will occur. So basically, our system in the example on screen there, where deposition velocity is 523 feet per second. We're looking for velocity rates higher than that. So in calculating the maximum limit velocity, there are four methods implemented in FluidFlow, and WASC is the default, generalized relationship, also known as Algren-Clift. A couple more available there as a function of particle size that uses the King formulas, Oroskar and Turian, and Schiller and Herbig. So Oroskar assumes a single unique size for the particle and the spherical type particle. So let's take a quick look at an example here. I'm just gonna move my FluidFlow over this share screen. So we have a system that is it's basically inlet flow rate here, and here's the way the settling slurries defined as heterogeneous settling, as opposed to Newtonian or non-Newtonian non-settling, pulp and paper stock, and two-phase being the other options. So heterogeneous settling with the flow defined as either solids only, carrier only, or total slurry flow. Then we go and select the solids database. So from the solids database, we select the actual solid. And I'll come back to look at the definition in just a second. Concentration defined by either volume or weight, CW or CB. And solids concentration percentage, let's say 20%. Use size distribution data, no, in which case we use D50 or D85, depending on the type of correlation that we're using here. And here are the units as well. On the bottom screen here, you'll see WASC, where my cursor is. So if we go for a second to options, non-Newtonian slurry, this is the heterogeneous settling slurry correlation currently selected. And as I said, this is the default one. And here are some other options here in terms of spherical particles, which by default is off. Also the deposition velocity, the VSM correlation using WASC generalized relationship. As far as the the solids database, so I'm just going to go to database solids here for a second. So here's Mica, and we got the solid density and bulk density, and the solid shape factor, and the bed sliding coefficient. Okay, so that's where you'd be inserting your solid properties to be considered in the mixture. So we are bringing into the network this amount of flow rate, so 41.7 cubic meters per hour. And there are a number of elevation changes here between these nodes. If I scroll down, and then eventually an outlet here. So if I hit calculate, so some of the things that I could look at here on the results tab, let's say for this pipeline, we have a composition mass percentage here. We have the actual loss correlation that we used. Here's the deposition velocity, 523, and the actual velocity in the pipeline. So out velocity at this node, 7.5 feet per second, about 50% higher than the deposition velocity. So we could, in this case, assume we're in a heterogeneous flow region, and no saltation will occur. Also, what we could show here is the solid delivered here. So if I go, say, not results unit, I deliver solids in kilogram per second. And let's look at visible results. And a number of output measures here. And I'm looking for okay, let's see, solids delivered. Can't seem to find that. Okay, composition mass. Okay, so somewhere here in this long list we have the solids delivered quantity. And let's try a flyby. Solids delivered. It's not in the list. Okay, let's select now. Select the output, the outlet here. So here's the solids delivered, 2.64 kilograms per second on this node, on this pressure node. Okay, so we're looking at the flow versus friction loss curve, where we can look at the RR distribution curve, and this is the D50 and D85. If we switch this to use size distribution data, then we're looking at the percentage retained for different mesh sizes, different screen sizes. And if we hit calculate here, you're going to see a message where we're using WASC, but WASC does not require size distribution. It requires D50 and D85, which are going to be extracted from the RR curve, which is in this case here. Right, so here's the RR curve plotted based on that size distribution. Okay, so there you go. Okay, so inlet again, total slurry flow by where the solid concentration is by weight, and we have the D50 and D85 values in millimeters, and we're looking at solids delivered result of 264 kilograms per second. Okay, so just going to move this aside for a bit. As I said earlier, if you have any questions, please type them in the chat window. Let's take a look at the non-settling slurries now. So basically, we talk about a very small solid particle forming a stable homogeneous mixture with a Newtonian carrier, but the actual mixture exhibits in that case a non-Newtonian behavior. So what we're looking at in this case is not a constant viscosity versus shear rate as it is for a Newtonian fluid, but one that is actually it varies, and there are different correlations available. Most commonly, these are the ones that FluidFlow has. Herschel-Berkeley, Power Law, Casso, and Bingham plastic models. These are the most common rheology models, and we have the ability in that case to define this viscosity in the fluids database in a couple of different ways. As a viscosity versus shear rate plot, so through constants based on the rheology data, or as, yeah, you can see viscosity here on centipoise, or as a table representing the shear rate versus shear stress with a specific curve fit type. So we can choose from the 4 type of correlations there. You can see the curve fit example there. And basically, we're trying to get the best fit between the measured points. Okay, looks like we're running out of time here. So briefly, here are a couple of examples. You can actually look at FluidFlow website, fluidflowinfo.com. So here's an overland transport system where Bingham plastic fluid is transported over almost 9 kilometers of pipework with changing elevation. On the bottom there, you can also see the composite chart of the 2 pumps in parallel. And another example would be a large red mud pipe flow system, again over 7 kilometers of pipework with 8 pumps this time. You can get a free trial of FluidFlow at fluidflowinfo.com website. Thank you very much for attending this webinar, and hope to see you at the next one, Modeling Gas Pipe Flow Systems, on October 22nd. Thank you all. I wish you a good day.